Well, welcome. In this video, we're going to be looking at lesson 11.6. The objective for this lesson is to make sure that we know how to figure out from an equation, how to get from that equation to get to a graph of a polynomial, and from that graph to determine how many of the solutions to that equation would end up being real solutions and non-real solutions. Well, before we do all this, since we're going to be working with some graphing, it's very important that you have a TI Inspire or similar graphing calculator because a lot of what we're going to be doing is going to be with the graphing calculator. So make sure you have one of those before starting watching this video. Okay, so there's going to be a lot of information that we're going to be talking about here. So to help us out, I've highlighted some things. So let's look at some of these pieces so you can understand what we're talking about. So first off, let's look at this box where it says a fundamental theorem of algebra. What it says there is that every polynomial that's set equal to 0 of any degree, as long as the degree is greater than or equal to 1, with complex number coefficients, so all that's saying is that we have coefficients that are regular old numbers, has at least one complex number solution. So how can we interpret that? All it's saying is if we have a degree of greater than 1, that there's always going to be at least one solution to that polynomial. And we're going to be working a lot with that idea, but more in specific terms with this paragraph here. So first off, the main thing that we make sure we understand is the degree of a polynomial tells you how many zeros or roots the polynomial has. Now remember, we've talked about degrees earlier on in this chapter. The degree is the largest exponent when the polynomial is in standard form. So again, that degree tells us how many solutions, how many zeros or roots the polynomial has. Now remember, we have some different categories of numbers. We have that there could be real and non-real solutions. So that is going to be the case with these problems. Some of them, the roots will be real solutions, some of them will be non-real. Or maybe all of them are real or all of them are non-real. And we're going to determine that by looking at the graph. Well, how is that possible? Well, for example, remember when we worked with quadratic equations in the form ax squared plus bx plus c equals 0? And we used a quadratic formula, and we found that when we know first off there's always going to be two solutions for those. And when we use the discriminant, the b squared minus 4ac, that told us what kind of solutions we were working with. So remember, if it was positive, if it was greater than 0, there was two real solutions. If it was a negative number that we got, so if it was less than 0, there was two non-real solutions, or what we could call non-real complex solutions. And if it equaled exactly 0, we said that there was one real solution. Basically what that meant is that when we would get it factored down, it would be the same number in parentheses twice, if you want to think of it that way. And what we can refer to that as is multiplicities. So for when it was exactly 0, we would say it was that one answer with a multiplicity of 2. So here we have some examples. So right here we have the equation x squared minus 10x plus 25. We could get that factor to be x minus 5 quantity squared. Now what that means is that if we set that equal to 0, we would get a root or a 0 of 5. But the fact that it's x minus 5 squared means we'd have x minus 5 times x minus 5. So technically we would get an answer of 5 twice as our 0 or as our root. So the way that we phrase that is you could say it's got a 0 of 5 with a multiplicity of 2, or you can say it's a 5 or it's a double root of 5. Either one of those ways of phrasing it would be correct. Personally, I like the first one there of saying it's got a multiplicity of 2. So in general, the multiplicity can be determined by the degree of the factor. Okay, so now originally we said that the degree of the polynomial, when it's in standard form, that degree tells us how many zeros or how many roots there are. When we have it in factored form, if any factors have an exponent, if any factors have a degree, that tells you the multiplicity. So if the degree is more than 1, that tells us what the multiplicity would be. Let's look at this. I'm going to scroll down here. So basically, this number of roots of a polynomial equation theorem is basically describing what we just talked about, saying every polynomial of degree n has exactly n roots. So whatever the degree is tells us how many roots there are. This little tree diagram here helps us kind of break this down as far as what we've talked about. Remember, the degree of the polynomial tells us how many total complex solutions there are. How many total zeros, how many total complex zeros, or how many total complex roots there are going to be. It can be phrased a number of different ways. You want to be familiar with all of them. And from the graph of a polynomial, we can look to see out of those total complex zeros, how many of them are real and how many of them are non-real. And we do that by looking at the x-intercepts. So the x-intercepts tells us the number of real solutions. How does that all work? Let's look at some examples and make more sense out of all that. Okay, so let's look at this first polynomial that's described by x to the fifth minus x to the fourth minus 21x cubed minus 37x squared minus 98x minus 24. So again, the first question is asking how many zeros does it have? And we get that, so since they're asking for the total number of zeros, we get that from the degree of the polynomial. And since this is in standard form, we can see here very easily that the largest exponent is 5. So since the degree is 5, there are going to be 5 zeros total. Now when it says how many of them are real, there's no way for me to get that just by looking at the equation. In order for us to get this, we need to look at the graph. So at this point, why don't you guys get out your graphing calculators, and we're going to go to a graphing screen. And from that graphing screen, we're just going to type in the equation. So the equation is x to the fifth. Now remember, when you type in an exponent, if you continue to type, it's going to be, everything else is still going to be as an exponent. So I want to move my cursor down. So I'm going to hit the arrow to the right. And then it's minus x to the fourth. And then minus 21x cubed. And then minus 37x squared. And then minus 98x. And then minus 24. And for this graph, we don't really care even what the x-intercepts are. All we care about is how many of them there are. So maybe we need to zoom out, because you never really know if the graph is going to be, if there's going to be other x-intercepts outside this window. So right now I can see that there's a total of 3 x-intercepts. But let's just double check. So let's zoom out here. Maybe zoom out a few times. Whoops. All you do is you just hit enter. You just keep hitting enter. And I can see that obviously this doesn't, there's no other x-intercepts. Looks like those are the only ones there. So that means that this has 3 x-intercepts. So since there are 3 x-intercepts, 3 of those solutions are real solutions, or the 3 of those zeros we could say are 3 real zeros. Well, remember, there's 5 zeros total. Well, if 3 of them are real, that means that there's going to be 2 non-real zeros. And if you want a visual for why that is, remember we had that tree diagram on the previous page of our notes. And so we discovered again that the total number of zeros were 5. So underneath there, the real and non-real have to add up to be that total. So if there's 3 x-intercepts, there's 3 real solutions. So that means there's got to be 2 non-real solutions. Okay, I want you guys to try this now on this next problem. So I want you to answer these 3 questions. And so do this on your own. Again, you'll need a graphing calculator. So go ahead and pause the video at this point and hit play when you're ready to check to see if you have the correct answer. Okay, so let's see how you did. So the previous one, or this one's just like the previous one, where the largest exponent there is a 5. So that means that the degree here is 5. So that means there's a total complex, the total number of complex solutions are 5. And again, to figure out how many of those solutions are real and non-real, we have to look at our graph. And so your graph would look something like this, or should look exactly like that. And that means that since there are 1, 2, 3 x-intercepts, that means that there are 3 real solutions. And if there's 5 total and 3 of them are real, that means 2 of them are non-real. Okay, so let's end by looking at these last couple of examples. It says, for each of the following factored polynomials, give the degree of the polynomial and the zeros with their multiplicities. Well, this is in factored form. So in order for me to figure out what the degree would be if it were in standard form, I do not want to have to multiply all this together. And we don't have to. What we're going to do is we're going to take each factor and we're going to figure out the degree from each factor and then add those together. So the degree for the first factor is 1. The degree for the second factor, so we get that here. The degree for the second factor is 3. And the degree for the last factor is 2. So if I add those together, 1 plus 3 plus 2 gives me 6. Now remember, we only get degrees if from the variables with their exponents. So if instead of x in front of parentheses, if there was no x in front of parentheses, but just like maybe like a number 8, you don't get a degree from just a plain old constant, from a plain old number. So we would not get a degree from just a number if it was in front of the parentheses. You want to be careful with that. But since this is a variable, an x, it does have an exponent of 1, so that's the degree of that first factor would just be 1. So now what we're going to do is we're going to list out what our zeros would be. So the total degree of this polynomial is 6. So to find what the actual zeros would be, we're going to set each of these factors equal to 0 and solve. So if I did that for the first one, I'd get, if I set x equal to be 0, I would have just 0. And remember, the multiplicity for this one is just 1. This is how you can write it when they ask for the zeros with their multiplicities. So the next factor would be x minus 4. So if I set that equal to 0, I'd get a 0 of 4. But remember, it's cubed. So that means technically I have x minus 4 times x minus 4 times x minus 4. So there'd be 3 of them. So we would say it's got a multiplicity of 3. And the x plus 2, if I set that equal to 0, I get negative 2. And since the degree for that factor outside the parentheses there is 2, we would say it's got a multiplicity of 2. So there are the zeros and their multiplicities, and the total degree would be 6. So I want you guys to take a minute and do the same thing for part B here. For this next one, I want you to find the total degree of that polynomial, and then I want you to find each of the zeros with their multiplicities. So go ahead and pause the video at this point and hit play when you're ready to check to see if you have the correct answer. Okay, so let's see how you did here. So let's first start by finding the degree of the polynomial. So from the first factor, we see that that factor has a degree of 2. The second one we can see has a degree of 3. And the third one has a degree of 1. So if I add those together, 2 plus 3 plus 1, we get 6 as the degree of our polynomial. And now to find the zeros, we set each of those factors equal to 0, and then use the degree for that factor to determine the multiplicity. So the first factor, x plus 3, if I set that equal to 0, I get negative 3, so it's got a multiplicity, and it's got a multiplicity of 2. X minus 3, if I set that equal to 0, I would get positive 3, and since that factor has a degree of 3, it's got a multiplicity of 3. And lastly, x plus 6, if I set that equal to 0, I get negative 6, and it's got a multiplicity of 1. So there you have it. That is it. That is it for lesson 11.6. So hopefully you see now how we can determine the number of or what kind of zeros we would have and what kind of roots we would have by looking at the graphs. And for this most recent examples, just if you have something in factored form, how to determine what the zeros and their multiplicities would be. So with that, good luck now as you work on your assignment.